I'm going to start by going over, I can't remember because I'm sure you told me, but I've forgotten. A homework question that essentially asks you to find the angle between two planes. So imagine this is plane 1 and this is plane 2, and we're trying to find this angle theta. And the way you do it is that the angle theta between two planes is the same to the number as the angle between the normals of the plane. So that's basically all you do. So if this plane here had a normal 1, 2, 3, and this second plane here was 1, -1, 5, can't you just use the cosine of theta dot product, off you go, and you can find the size of the angle. So the angle between the normals is the same number as the angle between the planes, which is kind of helpful.
Why is that, Mr. Robertson? Why is the angle between the two planes the same as the angle between the normal vectors?
I'm probably going to kill this picture. Can you imagine that's the normal to the first one, right?
Yes.
And where would I go? That would be this plane, and then this guy up here is a normal to the second plane, and this angle theta is the same as that angle theta.
Okay. Thank you.
It's hard to draw in 3D. It really is. So I'm not convinced that picture is convincing. And here's a guy over here. Suppose they ask you for the angle between a line and a plane. So they want this angle here. So how do you find the angle between that? So let's say the normal of the plane is 1, 2, 3, and the direction vector of the line, which is a different thing from a normal, is 1, -1, 4. I can find the angle between the normal and that. But if I find the angle between the normal and the line, I'm actually finding this angle, aren't I? So what little kink do you do at the end to find this angle, which is the one you're really after?
Subtract it from 90.
And you're done. Make sense? So it would be 90, take away the angle between the normal and the direction vector. Okay, is there any other questions, maybe homework questions like that that have cropped up that you want me to, you know, 2 minutes saves you 20 minutes, right? It's easier to, if you get stuck. You're good? Right. So I've got a little hit list here that I was making up before the class started, just to make sure I don't miss anything. We're going to look at today the properties of space curves. We've looked at quite a lot of them, but there's still some more to come. We're going to look at things called the unit tangent vector. We're going to look at things called the equation of a tangent line. And I think the last thing I need to do is look at finding integrals. So that's kind of my hit list of properties of space curves. Now, last time we looked into space curves, so let's do number 1 again. A space curve is essentially a guy that looks like this. An example of a space curve might be a helix. Just to get our brains working up, I said this is a helix. How do you know it's a helix?
Because of what?
Functions.
Because of what?
Because of what?
Function.
Okay, I'm going to say, Abigail, you can tell me. What are you saying first?
3 functions.
That doesn't guarantee it's a helix. It guarantees it's a space curve, but it doesn't.
The sine, cosine.
Yes, the sine and the cosine feature. That's what I was kind of getting at. Does that make sense? If you're a helix, you'll have a sine. It could be 2t, it could be 2 sine t, and you'll have another one, but it'll be a cosine, a 2 cosine, and then you'll have a third one. In this case, it's here. And when you look at this, you can tell it's going to be a helix. You can also tell which axes it's spiraling along. So yeah, it could be spiraling up the z-axis, but it couldn't be spiraling along the x, or for that matter, spiraling along the y. By looking at this one, which direction do you think the helix is going to be spiraling in?
The Z.
It-
Z.
Yeah, the Z direction.
Yeah, I'm hearing a lot of Z's. Do you know the correct pronunciation is Z? I just thought I'd put that out there. I'm just correcting your pronunciation. It is Z. Right. Remember, my language is older than yours, so I'm correct and you're wrong. It's Z, right? And people will say to me, "How can it be Z? How
The
do
same
you
way that
say?"
it's A, B, and C.
Yeah, or they say things like, "Well, how do you say zebra?" I say zebra. Right, so I don't, right? When you say zoo, what kind of sound does the Z make?
Zzz.
Right, it doesn't make a Z sound, does it? Well, maybe to your ears it does, to mine it doesn't. Anyway, it's Z. Oh, and the other one is J. It's not J. I've got a theory of how you change those, and this is a total lie, but it's a good theory anyway. Remember when you lot were British, way back in your history, and then you decided to rebel and become pains in the butt for a while? I think one of the things you did, just because you wanted to be awkward, is that you picked a couple of letters that you were going to spell or say differently, I should say. And so J and Z got the job, and then you used it to catch British spies. You'd get them to say the alphabet, and you know that Americans would say it one way and British spies would say it the other way, and that's how you caught us.
I read a article yesterday that said that Benjamin Franklin went around and just kind of edited a couple words after the revolution just to change things a little bit.
So he just wanted to be different for the sake of being different.
Yep.
Okay. Well, I still love yous, even if you are weird, as a nation. Okay. Focus, Donald. Right. Now, suppose I have the problem of what kind of rules work in Space Curve. Now, there are a number of rules that you got. Can you remember a rule called the product rule?
Yeah.
Remember that guy? Now, in the 2D world, you'd have a function made up of two guys multiplied together, right? And in the 2D world, the derivative of that function was f dashed g plus f of g dashed. And we call that the product rule. Suppose I want to find the derivative of this space curve dot product with this second space curve. So can you imagine I had a function like this and then I had another function t cubed, t squared? If I did the dot product of them, wouldn't I be ending up with 3 multiplications all added together? That's quite a messy thing. So what's the result? That dot is a dot product. Well, it is r dash t dot product with s of t plus r of t dot product s dash of t. Isn't that essentially the same kind of structure as a dot, as a product rule? Suppose I wanted to find the derivative of the cross product, oops, of 2. So the dot product generates this formula, right? The derivative of two space curves having a dot product applied to them gives you this formula. Now we're going to look at what do you think this fella would get you. Right, if the world was fair and math had a structure to it, wouldn't this answer have some structure to it which would vaguely resemble this thing up here? Because didn't the dot product structure pretty much reflect this here? So this is the first time anybody, probably unless you've taken this class together, will have seen this. Anybody want to have an inspired guess at what you think the answer might be?
Maybe perhaps R prime cross S plus S prime cross R, perhaps.
I think that's what you said. Agreed?
Yeah.
Yeah. And the answer is yes. That's exactly what it is. Most of the properties that we think of from Calc 1, product rule, for instance, transfers really well into dot product and cross product situations. The addition formula works. So we're doing a little bit of theory today, just at the beginning. If you want to find the derivative of two space curves being added, make sense? Differentiation is a process over it. I'm not doing them. There are tons of the darn things. What do you think K times R of T would get you? So you take a space curve and multiply it by a scalar like K. What do you think that would end up getting you? K times R dashed of T. You know, like 5x squared is the same as 5 times the derivative of x squared, right? So if you come across a kind of generic thing and some, you know, when they try and prove some things, especially when they prove them in space curve world, they may well resort to using some kind of algebra of calculus to just reduce the workload a little bit. And if you wonder what the heck is going on, they're just using product rule on a dot product or on a cross product, which kind of gives you an idea why they stuck the word product in the name of them. And that's what they do. So that's number one, properties of space curves. Just want to show you the generic rules of, and there's many, many more of them that you could do. Now, this is a new guy. It's called a unit tangent vector. We haven't done him. Okay, suppose I have a space curve, t squared e to the t cosine of 2t. And let's just say, for argument's sake, that e is just a, you know, some ziggy-zag curve that looks something like that. Imagine I was looking at one point on that curve, that point there. That would be my derivative. Remember the roller coaster story that you shoot off to your death? That would be this vector here. Right? So the unit tangent vector at any given point t is given by this formula. Capital T to mean unit tangent vector. So if you ever see a capital T anywhere in any textbook, the convention in the world is unit tangent vector. There are actually going to be two others that you'll eventually discover, called the unit normal, and the third one's called the unit binormal. But right now, we're only going to look at this fella, the unit tangent vector. He is 1 over the magnitude of the vector t, so that's a scalar, r dashed of t. So what is the unit tangent vector? Can you imagine this red vector is the derivative vector, right? It's the guy that you got. The unit tangent vector is a guy that's parallel to this, but whose length is 1. So what they're doing here is that they are standardizing the derivative so that when you look at the derivative of a curve, a space curve, at one given point, you're going to be looking at that direction as a unit tangent vector. Because typically when you do a normal r dashed of t, don't you get sometimes a really long vector and sometimes quite a short vector? Can you remember what we said yesterday? The magnitude of this vector was telling you about your roller coaster death. The derivative was just basically telling you, where are we? Here we go, down here. The derivative was telling you this vector. But what was the magnitude of this pen telling you?
The speed.
The speed. See, as you shoot off the roller coaster at this point, you could shoot off at 200 miles an hour, you could shoot off at 2 miles an hour. The length of that vector. So if you calculated r dashed of t and that happened to be at t equals 5, won't r dashed of 5 be a single vector of a particular length? And the length of that vector is the magnitude, the velocity's speed, I should say, right, at that point. So this is basically reducing everything to being a length of 1. Well, the application's a lot easier than maybe the way I'm writing it down. So let's go back to this fella here. And we are going to find the unit tangent vector at 0. So that would be the question. Find the unit tangent vector at 0. So step 1, you find the derivative of your space curve. 2t e to the t. Okay, this one catches so many people out, catches me out as well. I'm differentiating the cosine of 2t. It's equal to something, right? What's it equal to?
Is it negative sine? Negative 2t. Negative 2 sine 2t.
Yes. Because you've done so much differentiating, yeah, wipe the sweat off your brow. Because you're doing so much differentiation here, and then integration, don't sometimes with trig functions especially, you get back to front and upside down. You sometimes forget which one's plus and which one's negative. And is it a times 2 or is it a times a half, which is the other mistake you can make. But in differentiation, everything is multiplication. And in integration, everything, well, I can't say everything is dividing, but you know, the sine of 2t gets you a half, a negative a half, cosine of 2t, for example. Well, then, that's the derivative. Then you find the numerical value at t. So, plug in 0. E to the 0 gets you 1. That guy is 0. Oh, what a very bad choice of question. So let me cheat. Plus t plus 1 plus 1. This vector ends up being that fella there. So how do I get the unit tangent vector? Well, can I tell you that the magnitude of this vector is 2? But you could imagine square root of nothing squared, 2 squared, and so on, gets you 2. Then the unit tangent vector at 0 would be the vector 0, 1, 0. And that was a bad question because the numbers aren't very interesting. So I'm going to do a second version of that same puzzle. I'm going to make my life hard. It's going to be t cubed plus t.
Sorry, can I see
Yes.
that old?
This one is basically a half of that guy. I just did the whole thing in my head because the numbers were too easy. You're breaking up a little bit. Okay. Let's do another one where you actually get to do some stuff. Right. I need to differentiate this space curve. That means I am going to have to wipe some cobwebs out of my brain for at least some of these. This one here is just multiplied by the power, reduce the power by 1, and you got that guy. How do you differentiate TE to the T?
2TE to the T.
Product rule.
It is product rule. So it depends on how you want to do it, but you do 1 times e to the t plus t times e to the t. Right, that's the product rule. If I wanted to differentiate 4 over the square root of t, wouldn't I have to do a bit of algebra on that before I even try and go near it? Great. So as a side note then, maybe I'll put it down here. You have to call it a fractional power of t. Are you comfortable with that becoming this, or do you need to see what I did to get that to happen? Okay. Now you can differentiate. Multiply by the power, and then reduce the power by 1. And then you should try and make it look as pretty as you can. And I call that style points. But essentially, the rules for style points are make the answer look like the original question. Didn't the original question have a fraction and a square root in it? Shouldn't this ugly thing be turned into that? Because that's how it originally started life. So this fella here is now that guy. Oh, and let's imagine for this second version that they wanted the unit normal at t equals 1.
Hey.
Or they could have just said find that, okay? Well, I find the derivative, the space curve's derivative at 1. 3 ones, so that's 4. E to the t plus e to the t, so that's 2e. And this guy here is what, -2? There. A much uglier looking answer, something we can get our teeth into. This is the value of the space curve at 1, right? I've replaced all these guys with 1, and hopefully that's the answer. So far, so good. Now, I need to find the magnitude of it, which is 4 squared, 2e squared, plus -2 squared. And the magnitude of this guy then is square root of 20 plus 4e squared. Nice ugly answer. Right. So the unit normal at 1 is 1 over the magnitude of the vector times that vector. So it's going to be 1 over the square root of 20 plus 4e squared. And the vector is 4, 2e, -2. And I guess for completeness sake, then I should combine these into a single vector. And now you've got as exact values that answer. is there any way I could have simplified? You're going to have to hit the space bar if you want to talk. Is there any way I could have simplified the square root of 20 plus 4e squared?
2 root 5.
So pull out a 4 as a common factor, which gets you 2. Agreed? Now, what would the effect be in my answer? Well, that 4 would cancel out with this 2, and you would then get 2 over the square root of 5 plus e squared, e over the square root of 5 plus e squared, and finally negative 1 over the square root of 5 plus e squared. And as far as I can tell, when you write the answer to questions like these, you don't even use this notation, don't you use the IJK notation almost exclusively. I think it's because maybe it's easier for the computer to handle it. It does give you the added annoyance, for want of a better word, is that you do this question correctly and you get this result, but the software was wanting that result, and so it says you're wrong. And you're not really, you know, you're 99% right. You're not really wrong at all. Okay, so to get a unit tangent vector, you find the derivative of the vector at that point. You then get the magnitude of that, and you reduce your guy basically to a vector whose length is 1, and that we call the unit normal vector. Are we cool with that? Okay. Do you want me to do another one, or are you comfortable right now on moving on? Because I kind of gave you the easy one first and a horrible one second. I guess I could put an average kind of level one in the middle.
Okay, so that was unit normal rather than tangent?
That is a unit oh, darn it. It is a unit tangent. My apologies. I know where that came from. Remember I said there's one called unit normal and one called unit binormal? My brain just went over. The guys that we have just been calculating are the unit tangent vectors. So let me say that again. The guys that we are calculating, these guys are called the unit tangent, not the unit normal. My brain was somewhere else, I think. I'm glad someone caught it. It's a unit tangent. And after saying that, I think I better do one and call it the right name. Suppose we are being asked to find a unit tangent. At 0 of this function. Three sine t e to the t squared plus t and 4 cosine 2t. So the process was correct. Everything I did was correct. The only thing I did wrong was give it the wrong name. So to get the unit tangent, we'll differentiate this guy, 3 cosine t. If you differentiate e to the t squared, what method will I use to differentiate e to the t squared?
Chain rule.
Yeah. So the answer would be e to the t squared times the derivative of t squared, so it would be that guy. So what I do, that's like basically step 1. In step 2, you evaluate your derivative, in this case at 0. And 3 cosines gets me 3. That gets me nothing plus 1. And that guy there gets me nothing. And then in the third step is I find the magnitude of this derivative, which is what? The square root of 10. And then I can get not the
Quick
unit
point.
normal,
Wouldn't,
unit tangent.
Wouldn't the 2t e to the t to the 2, wouldn't that be 0? Because, no, the second
Yeah, that would be 0, but plus 1 because of this
Oh.
extra term.
one. Okay, good.
Yeah, but don't worry, I'd rather people do that because you know I make mistakes. This particular time it wasn't, but a lot of the time you're right, I do things like that. So we got this fella, it's root 10. So to get the unit tangent, it's 1 over this fella times that, which becomes 3 over root 10, 1 over root 10, 0. And again, I'll make sure I say the name enough times today. The unit tangent is this guy. Let's do the awkward thing. You type this into the computer. In fact, you won't. You'll probably have to type this into the computer. And this is a deliberate mistake. What's wrong about what I've just written?
You'd leave out the K.
Yeah. There's none of it, you shouldn't bother with it, right? Convention is, if there's no X's, you don't say X, right? Now, I would hope that the software is clever enough to recognize that that is correct. But it might not be, in which case you'll do that. Has anybody did questions, maybe some of the earlier questions that this has happened and they had to rationalize the denominator? Or did it take the kind of this version, or did you have to do that version? Has
Had
anybody
to do
experienced it?
one with the rationalized denominator.
Right, and it didn't take that answer and you had to fix it, essentially?
I can't remember, but I think there was one where I had to put the square root on top.
Right. So just be on the lookout for that, because you're going to do some complicated questions. One that comes to mind, right, this guy here. You may be doing a complicated question and it'll tell you you're wrong, and then you think that you're screwed up in a major way, and it might just be a simplification thing and it's not really a big deal, but you don't know because you just know you're wrong and you're not sure why.
And one thing I've
Generally-
noticed.
Right,
Oh, go
question?
ahead.
Oh, no, go ahead. Sorry.
Well, one thing I've noticed in WebAssign as well is you notice how there's a lot of questions that have a, practice another option there.
Yeah.
If you're getting something like that and you're kind of unsure of the input method that it's asking for, I actually already got into the habit of using that, so I'm not burning my attempts. And, I practice a like problem, solve it the right way, and then play with different ways of inputting it and see what it'll take. Not all problems on there have it, but some do. And that's kind of a way that I've noticed so far when I had a problem with one of the ones in the very first homework to sort that out.
That's what I was going to say. If I miss the first question and I don't want to burn, and I think I did it right, and I don't want to burn answers trying to figure out how to correctly answer it, I'll just use the practice problem and solve that and then kind of play with that.
That is good advice. Yeah. So I'm going to assume now that if I call it the right thing, unit tangent, which I've been doing, that we're comfortable with this process, right? So they'll give you a space curve and they'll say, find a unit tangent at 0, find a unit tangent at t equals 1/2 or whatever. And it's pretty much differentiate, plug in a number, get the magnitude, and then put them together, right? So let's look at what is called, and it is called this. Actually, it's called the right thing over here. The equation of a tangent line. And I guess I'll add in 3D. Well, let's look at the analogy of what that might look in 2D. In the good old Calc 1 world, and you had a point here, that red line would be called the tangent line, right? And there were questions where you had to find the equation of that tangent line. And when you did, it ended up being something like that, right? Now, when you went through the process of how did you get the equation of that line, wasn't the first step that you found the derivative? And let's say that this x was at x equals 3, just for argument's sake. Then didn't you find the derivative at 3 because that gave you the slope? And then from there, didn't you do, depends on what the question is, but didn't you do some kind of equation where you used the coordinates of that point, which would be what, 3 comma whatever it is, right? And get the equation of the line. So there was a kind of find the slope, right? And then, well, find the derivative first, use the derivative to get the slope. Once you know that, you've got a point, you've got a slope, point slope equation, equation of the tangent line. Right. What would that look like in a space curve world? Well, this is our space curve, R of t. If I gave you a point on that curve, where am I going to go? I'm going to give you this point here. So when you tell someone a point on a space curve, don't you just tell them the t value, right? At t equals 2 or t equals 20 or something, right? So you'll be told, say, at t equals 3, right? And let's suppose you know the space curve, and it's t squared 2t 8, just because I want it, right? Something like that. We are being asked to find the equation of the tangent line. Now, in 3D, won't the tangent line just be a line in 3D? Now, when you want to find the equation of any line in 3 dimensions, don't you need to know 2 things? The first thing you need to know is a point on the line. And the second thing you need to know, we call it the direction vector v. If I know those 2 things, can't I write down the equation of the line pretty easily? Right. Well, if you're being asked for this space curve here to find what the equation of the tangent line is at t equals 3, let's see if we can find these 2 things. Well, let's find the point first. Well, if you plug 3 into here, you'll get 9, 6, 8. Doesn't that transfer, because this is a position vector, doesn't that transfer into the point on the curve? So that point there would be 9, 6, 8. So we're halfway there. How do you think I'm going to find the direction vector for this tangent line?
If you take the derivative of it, isn't that just giving you the instantaneous velocity of the...
Right, which is essentially the direction vector in the context of this question. So I will find r dashed of t, which I get is 2t, comma 2. What's the derivative of 8? Yeah, big fat 0.
0, or...
Yeah, 0. And then shouldn't I evaluate it at 3? So what do I get? I get 6, 2, 0. So I will be able to give you the equation of this line now. I know it passes through the point 9, 6, 8. I know its direction vector is 6, 2, 0. let's call that 8t. No, I can't call it 8t anymore, darn it. I should think more before I randomly create questions. I have an issue with this. It's not a big issue. It's just a 0. Let's do it then. I'm going to have to call it something, aren't I? No particular reason I can think of. I'm going to call it U of t. And it is going to be 9 plus 6t. 6 plus 2t. And this 0 was bugging me, but really it doesn't. It's not a big issue. Isn't it technically 8 plus 0t, but you don't put 0t in?
The new point is at for Z is 24.
Yeah, I've decided not to bother. I've just decided
Oh,
to bite the bullet. I just didn't want the first question to have a 0 anywhere. But I think about it, it's not that big a deal, isn't it? You know, if one of the components of the direction vector is 0, doesn't it just mean you don't get any t's in it? So the equation of a tangent line is very analogous to what you did. You find a derivative. When you plug the number in, instead of getting the slope, when you plug the number in this case it was 3, in my case here it was also 3, don't you get a direction vector instead of a slope? And see the equation that you use to get the equation of the line in 2D, isn't it a different kind of equation when you do it in 3D? But nonetheless, it is an equation. Remember, x naught plus at, y naught plus bt, z naught plus ct. Try this. Here is a space curve. And the question is, find the equation of the tangent line at t equals 0. Okay, you got 3 minutes, go for it. And then I'll do it. I'm going to disappear from this and I'll take the class register while you're waiting. It gives me a chance. Yeah. I have got you. I will try and be more careful. About 30 seconds and then we're ready to do this one. Okay, here we go. Got this fella? First thing I am going to do is find his derivative, e to the t. And this one is a very simple product rule. So you get 1 times e to the t plus t times e to the t. And don't forget to differentiate the plus t, so there's an extra +1 at the end. This one here could catch you out. And the answer isn't 1/e to the t, although it's very close to being that. Agreed? What's missing?
Natural log.
No.
So it's going to be -1
Yeah.
over e.
I can see why you might think that. I want to put it somewhere out his way. I want to keep this for just a few moments. This is how you should look at this guy. Right, when you see him that way, you can see it's just a very simple, essentially chain rule. E to the negative t times the derivative of negative t, which is just -1. And then for style points, convert it back into the original look. So that would be my step 1. My step 2, evaluate it at, in this case, 0. Kind of chose it so these would come out as nice numbers. So that e to the 0 is 1. That'll get you 1, that'll get you 0, that'll get you another 1. So there's 2 there. And I believe this one here will get you -1. Great. Find the magnitude of this vector. And no, we don't. I almost forgot what we were doing here. We then find its position. So what's that going to be? Its position is e to the 0. 0 plus 0. And 1/e to the 0. So its position is 1, 0, 1. So we have the point 101, and the derivative tells me that the direction of this line is that. And if you want to put them together, the equation of the line, which I'm calling u of t, is 1 plus 1t, nothing plus 2t, and 1 take away t.
The only thing I'm wondering is, I don't know why I can't. How do you get the +1 in your derivative in the y coordinate?
+1 in my derivative here, because of this piece here, right? Just an extra little.
Oh, I didn't see the +t.
Yeah. Well, as you know, I never make mistakes, so I don't know how you could possibly do that. Yeah, you should laugh. There are a number of mistakes I make. I think the older I get, the problem with my brain is that I'm already thinking 2 lines ahead of where I should be, and that's not good for somebody my age, because then you forget line 3, and then you get confused to yourself. But essentially, there is a nice process to these questions. You agree that, you know, here's a space curve, here's t = 2, and off you go. Now, I'm not going to do the next question in full. I'm just going to give you a weird version of that same question with a little kink in it that might throw you. So suppose you're given a space curve. And they ask you to find the equation of the tangent line at the point 2, 3, 3. So they don't ask you to find the equation of the tangent line at t = 5 or t = 0 or t = whatever the number is. They ask you to find the equation of the tangent line at the point 2, 3, 3. Now, in a lot of ways, that's helpful, because isn't that one of the 2 things I want? The problem is, don't I still need to know what t value this is? Because don't I need the t value to plug into this derivative to get the direction vector? So I guess the question now becomes, how do I find the missing t value so I can continue with this question?
You set one of the values equal to its point component, so like the 3t equals 3.
Oh, that would have been a better choice.
Yeah,
Let's
Just
do
by
that
looking
one.
at it, I think you could see that it's 1.
yeah, but that's
Yes,
gonna be one.
it is definitely one. I was playing safe here when I was creating this question to make sure the numbers were easy to do in my head.
Yeah, the Z component makes it pretty easy to spot.
Yeah, the Z is probably the easiest of the three. Can you pretend this question was harder, just so I can show you the process?
Okay,
for
1 plus
something
1
that,
equals.
yeah, that kind of thing, right? So just make the x's equal, and you get this, which becomes this question. And then if you solve this question, you'll find that very often in the more difficult questions, there might be a choice. Do you see in this case right now, there's 2 choices. And then what you do is you would go to the second equation, which is 2t plus 1 equals 3 in my case, and that's 2t equals 2, and that's t equals 1. But can you imagine that this one also gave you 2 choices? Right, in a different world. So can you imagine we did a different kind of question, and it said t is 7 and t is 1. When you look at this one and you look at this one, do you see that t equals 1 is the only one that's actually going to be of any use to you, because it's the only one that's true for each of them? Now in this question here, the numbers were very simple, so you could bypass that process. But if it gets to a quite messy one, where it's not obvious what the t's are, because you can't just look and say, oh yeah, if 3t is 3, t had to be 1, right? If that's not staring you in the face, you may well have to do this structure. So I'm just showing you, this is the process of match the x's and solve, then match the y's and solve, and you should by that point be able to identify a unique value of t. And then you go on and you do all the good stuff. Do you want another example of equation of a tangent line, or are we comfortable with the process now? I stick thumbs up. Why don't we do it as a vote? If you're happy, stick your thumbs up. If you're not happy, I won't see any thumbs, and I am good. I'm getting some visual thumbs and some virtual thumbs. We are good. We are moving on then. Oh God, the whole screen's filling up with thumbs now. So what we're going to do is the last thing on my list, and then I'm going to look at some homework questions, and we'll see where we can go from there. We talked about how do you integrate a space curve, like that guy there. Let's suppose it's integral from a fixed number to a fixed number, which is most likely going to be the case. So if the space curve, for instance, was t squared sine t e to the t, for example, then if you want to define it, and you want to do it from 0 to 1, yeah, it's quite a nice number, from 0 to 1 of this particular fella. Didn't you just break it into 3 separate integrals? And so you'd get the integral from 0 to 1 of t squared, then the integral from 0 to 1 of sine t, and then the integral from 0 to 1 of e to the t. And when you integrate, numerically integrate, so when we're finished, this is going to have numbers. Isn't the integral of a space curve a vector in 3D? So it's not got the same kind of interpretation that it did have a way back in Calc 2, whereas when you integrated, you found what we said was the area under the curve, right? It was an area, it was a scalar. Now we get a vector. So let's see what this fella looks like. This guy is 1/3 t cubed evaluated at t equals 0 to t equals 1. This middle one is negative cosine of t evaluated at t equals 0 to t equals 1. And this last guy at the end is what? Just e to the t evaluated at t equals 0 to t equals 1. Okay, a third takeaway, nothing gets you third. Yeah, negative the cosine of 1. Takeaway, a takeaway means you add, cosine of 0 gets you 1. And this fella gets you what? E, takeaway e to the 0, which is 1. Okay, it's not the prettiest answer in the world, but that's what the integral is. I would probably call that 1 takeaway cosine 1. Same kind of question. I don't get to see the same version of Webersine that you get. That trick of, do they want you to write 1 takeaway cosine of 1, or do they want you to write 0.123, the decimal version of that? I guess you will find out by doing that little practice test one if they give you one, you know, and try out both versions to see which one they're looking for. Are we cool with this process? Integrate each of the 3 terms separately from each other using 0 to 1 as the limit for each case. No big issues? Good. I'll do another one just basic like this, and then we'll look at some working backwards kind of thing. Right, suppose I'm being asked to find the integral from 0 to 2 of t e to the t 4t cubed and t plus 1. So I'm going to have to find 3 separate integrals.
Mr. Robertson, when you
Yes.
once you finish solving the integrals, what does it mean? How do you interpret it? Like,
The vector that you get out of this integral is essentially the average direction in which the curve is pointing over that interval. It's not a very satisfying definition, but that's what it is. So if you can imagine, this is t equals a, and then you finish at this point, this is t equals b. Can you see that this curve, this space curve is pointing at different directions from a all the way to b?
yes.
This single vector might be a vector that looks like this. And what it is saying is that the overall average direction that that thing is pointing in is this vector. It does have an analogy in the 2D world. Can you remember finding what was called the average value of a function? And it was described by this formula. Do you remember that guy?
Yeah.
Right. In the 2D world, you would be talking about the function starting here, the function finishing here. This bit is the area under the curve, and then you divided it by the distance from there to there, and what you got was essentially a horizontal line that told you the average value of the function. So in the 2D world, you're finding the average value of the function. In the 3D world, you're basically finding the average direction of its position vector.
Thank you.
Okay, I have a problem here, and at least you should have the same problem with one of these guys, this one. But let's get this guy out of the way. This is t to the 4, right? That's what that comes. So 2, 4, 8, 16, so that's what you'll get. This is a half t squared plus t, so that'll get you 2 plus 2. This will get you 4. How on earth am I going to integrate this guy?
I'm going to use the integration by parts.
Right. Now, there are two versions of integration by parts. There's the U, V, dv people, and there's the F dash capital G people. They are different ways of doing the exact same thing. So depending on who you've got, you're going to get the integral to that, and we will be done. So let's see if I can do it my particular way. You're going to get t, e to the t, take away e to the t, evaluated at t equals 0 to t equals 2. I'm trying to do that on my head. Hopefully I didn't screw up. Is someone doing it before me? You got the same thing? Guess the answer should be yes. I should be able to check it anyway if I differentiate it.
Yes.
Yeah, it works. Okay. So I now have to put 2 into that. So you get that guy, take away that guy, take away a nothing, take away a -1. So that becomes a +1. So this fella here is the integral of this space curve between 0 and 2. Kind of messy front guy, but 2 reasonable numbers after that. So you are going to be given integrals of lots of things that you probably haven't integrated in a while. So I'm going to just talk about individual integrals, but essentially Calc 2 stuff right now, to see if you can remember some of them. Integral of secant squared.
It'd be a secant tangent.
Nope. But keep going. Integral of secant squared. See, this is the rusty part because you haven't done it for 6 months. Say again?
Tangent. It's
Well
just
done.
tangent.
It's just tangent,
Well,
right?
tangent
Plus C, I guess.
plus C, yeah.
The plus C's probably won't matter because all these integrals are going to have, you know, from 0 to 2 on them anyway, for the majority. So,
Excuse me.
yes.
That previous problem back for a second.
Yes. Here we go.
Thank you very much.
Okay. How about, I don't need the answer to this one, but could you tell me how you would get the answer to this one, which is more important? Oh, we are in trouble. We are in trouble.
Well, I have a table of standard integrals.
I guess that would be the engineer's solution to the problem. There's a table somewhere with the answer I want in it, right? Okay. And basically, don't you write it like that and do U sub. Right. Okay. If you had to integrate that guy, it is a U sub. What would the U sub be that you would use to solve that question? I don't need to know the answer.
Everything in the square root. So
yeah.
T squared plus 1.
Correct. This question might be an integration by parts, but it might be a U sub. But only one of them would work.
U sub would probably be easier, or actually work.
Actually, the only way that would work in this case. And it would, of course, be T squared. I mean, you're getting a crash course on remembering how to integrate here.
There's a couple ways you could do it, but it's all going to involve u sub. You could break the sine up into 1 plus cosine squared, then make everything cosines. Or
You
you
could, but in this case, that would be probably a bad direction. So rewind that thought and just stick to a u sub.
yep, just say that sine is u, and then derivative would be negative.
We'll say that would end up being the integral of u squared when you're finished. Looks similar, totally different method. There is a way to integrate that guy. It does not involve u subs. It does not involve integration by parts. It involves something totally different.
Probably don't want to make that a triangle, maybe?
Oh, like in an x sub? You use that identity. Cos squared can be written as a half 1 plus the cosine of 2t, and sine squared can be written as a half 1 minus the cosine of 2t. So you know that it's going to be, the devil is in the detail in these questions, right? You know you're going to integrate three things, but then don't you need to know how to integrate things to be able to integrate three things? So you might get an ugly term like this or an ugly term like this, and you're going to have to use u subs, trig identities, table of values. That would be a sensible approach for some of the messier ones. But we need to know how to do these things, or else you won't be able to complete the question. Little side issue while we're here. I'm a great believer in that anything you learn in math will eventually come up. So, off the top of my head, quadratic formula. When was the last time you used quadratic formula in maths? Ages, right? And years go by, and in your third year at university, you hit a question where you have to know how to do the quadratic formula. Or you don't do integration by parts for ages. Right? And then 2 years later, there's a question appear. We assume that when you get to any part in the math, that anything that's happened in the past is fair game. So it's totally acceptable that you could get an integration that you might only have done 4 or 5 examples of in Calc 2 because there's so many different examples that you need to do. And being human beings, we're not very good at remembering things if we only do them a few times. And then suddenly you're thrown into the, oh God, how do you integrate sine squared? And so there might well be a couple of stressful times, but you know, it happens to everyone. So I'm going to give you a puzzle, and we're going to solve it. Suppose I tell you the derivative of a space curve is that guy. And I tell you that the value of this fella at 0 is a vector, this position vector, 0, 1, 2. And you're being asked to find that guy. Before we tackle this question, let's look at what that might look like in good old-fashioned, you know, Calc 1 and 2 world. You remember getting questions that looked like this. You remember seeing things that look like that? Isn't this the equivalent of that problem? If I was doing this question, how would I find f of x when I'm told what f dashed of x is equal to, what its derivative is?
Oh, you're just going to integrate it and then add a plus c. Or
Okay.
need to
Yes.
add this one.
Integrating a plus c. And won't this guy here allow me to figure out who the plus c is? Well, let's look at that and do the same thing. So I have a t squared, 2t plus 1, t cubed. If I integrate this fella, won't that be the guy I'm looking for, right? So I'm going to integrate each one of these fellas and see what I get. That guy is going to be 1/3 t cubed plus an unknown constant, which I'm calling c1. This guy is going to be t squared plus t plus an unknown constant, which I'm going to call c2. And this fella here is going to be 1/4 t to the 4 plus an unknown constant c3. So I get 1/3 t cubed c1, t squared plus t c2, 1/4 t to the 4 c3. And then I use this fella to figure out what the values of c are going to be. Because they won't all be the same number. Do you notice that they're called c1, c2, and c3? Because aren't you integrating each one of these independent of each other? So the arbitrary constants could well and probably will be different values. So you indicate the difference by not calling each of them the same plus c, but calling them c1, c2, and c3. Now, if you plug in 0 here, you get nothing cubed plus c1, which is c1. Nothing plus that guy, you get c2. And nothing plus that guy, you get c3. And won't that equal 0, 1, and 2? And if I do a quick match then, do you see I got really quite nice question because all the C's ended up being was 0, 1, and 2. And you put that together and you've solved your problem. R of t then will be 1/3 t cubed plus c1, which is nothing. The middle term is going to be t squared plus t plus c2, which is 1. And the last term is going to be 1/4 t to the 4 plus this guy. We good? Any questions about that? Are we feeling comfortable? Right. Suppose the derivative is 1 over t squared t sine t e to the t. Suppose it's 0, because 0 is a nice number. It's 1, 2, 3. And we're being asked to find what unique, because there's only one space curve that this will be true for, what unique space curve has a derivative of this and a position at 0 of 1, 2, 3. So we are going to have to integrate 1 over t squared. We're going to have to integrate t sine t. We're going to have to integrate e to the t. See if I can do these relatively quickly. If I wanted to integrate 1 over t squared, it's probably a good idea to call it that, right? And then I can use the power rule. Add 1 to the power, divide by the new power, and then make it look pretty. Oh, darn it in space. Do you know what my problem is? And someone mentioned earlier I shouldn't do this, and I just did it by sheer bad luck. What's going to be my problem?
You're gonna be dividing by 0.
Not a good idea. So I got to figure a way to fix this very quickly. And I will fix it by simply pretending that that was the value at r of 1. Hey, dodged a bullet there, right? So now I can do this. It's going to be negative 1 over t. Okay, what about t sine t? What's that going to look like when you integrate it? Well, it's going to be integration by parts. Depends how you want to do it, but believe you get t sine t, take away cosine t. And that guy, there's your third one. So far, so good. Now, I can now plug in 1. So this guy becomes negative 1 plus c1, so I dodged that bullet. Of course, I'm going to get an ugly guy now. I'm going to get the sine of 1, take away the cosine of 1, plus c2. And this guy here, I'm going to get e plus c3. And we're told that this is 1, 2, and 3. So when we match the x's, we match the y's, and finally we match the z's, we will be able to find out who each of them is. So if you match these two, negative 1 plus c1 equals 1, that tells me that c1 is 2. If I match these two, I know that the sine of 1, take away the cosine of 1, plus c2 is equal to 2, which means that c2 is just this ugly term. And then if I do the last one and match this fella with this fella, what would I get? I get this guy equals that, so c3 is equal to 3 take away e. So that's what c3 is, that's what c1 is, and that messes what c2 is. So if I go to here, because I've run out of room, can you imagine me just writing negative 1 over t plus 2, all of this plus this fella, and e to the t plus this guy, and we're finished.